So we've been looking at operations of complex numbers in rectangular form, converting them into polar form, which is also known as trigonometric form and exponential form. Looking at operations of those, now we're jumping into another operation. DeMoivre's theorem helps us do that, which is raising a complex number to a power. So what DeMoivre's theorem says is if you have, let's say, some complex number z, which is equal to x plus iy, and polar form, we find that it was the modulus of z, which is r cosine of theta plus I sine theta. Well, DeMoivre's theorem says if you're going to raise z, that complex number, to a power n, let's say that n is an integer, then the theorem says that this is the same thing as taking our modulus r, raising that to the nth power, all times cosine of n theta, so our exponent times our angle, plus I sine of n theta. Which makes sense if you go back to multiplication. So if we had z was equal to x of 1 plus I, y sub 1, w is equal to x of 2 plus I, y sub 2. We saw, actually, no, let's just not even do that. Let's just say that we wanted z squared. And we wanted to find z squared. Well, we knew that z here in polar form, which I just wrote out, this is where that form I was telling you, we can write it as, you might hear it as cis theta, or cis theta. That's just cosine theta plus I sine theta. So doing this might be where it might be helpful to write it in that shorthand. So this would be r cis, I did that, theta. And if I wanted z squared, well, this is r cis theta, technically, right, times r cis theta. But if we were multiplying, remember the rule was, this was the same thing as r times r squared, cis, we added our angles. So theta plus theta is 2 theta. So now if I multiply that by another z, you can see that, so if I took z squared times z, notice I would look at r squared cis 2 theta times z, which is r cis theta, using rules of addition. I'm sorry, using rules, if we're multiplying two complex numbers, we add our angles, and we have r squared times r is r cubed cis of 3 theta. So we can see that as we go down and we have the nth power, this is going to be r to the n cis n theta. So let's look at that. So if we started out and we had 2 cosine of pi tenths plus I sine of pi tenths, and this was all raised to the 5th power. So in the example, it says write each expression in rectangular form, x plus iy or yi, and in exponential form. So before we do that, let's first rewrite this. Let's perform the operations and then we'll convert it. So by DeMoivre's theorem, this is the same thing as 2 raised to our power of 5. Basically, we can say this is the same thing as cis, cosine theta plus I sine theta of our angle 5 times I/10. So 2 to the 5th power, if you multiply 2 times 2 times 2 times 2 times 2, you get 32. And this would give us cis of pi over 2. Okay, so there it is in polar form. In rectangular form, actually, let's first do exponential form. This is going to be 32 EI to our angle, which is pi halves. And then in rectangular form, let's first rewrite this out. We had 32 times, well, the cis was cosine of pi halves plus I sine of pi halves. So let's go back and evaluate those trigonometric functions at those angles. Those are ones that you should know. So we have 32 cosine of pi halves is 0 plus I sine of pi halves is 1. So in rectangular form, this is equal to 32i. So DeMoivre's theorem gives us a way, instead of having to take something, multiply it out 5 times, a lot faster and easier. If we had to do that in rectangular form and multiply out that, well, this is a case, it wouldn't have been as too bad because it's only one term, but 32i times 32i, and do that 5 times, it would have been kind of messy, especially if there was 2 terms in there and we had to distribute. So this is just an easier way to do operations of complex numbers. So the next example, we're given the number in exponential form, the complex number. It's root 3e. E is raised to the I times 5 pi 18th. And then that is all raised to the 6th power. So the reason why they give us exponential form is exponential form, it's easy to manipulate. So if you remember your rules of exponents, remember power to power, we multiply. And so now we can do the same thing here. We have this raised to a power of 6. We want to raise each piece to that 6th power. So we're going to take our root 3, raise it to the 6th. And we're going to take this EI 5 pi to the 18th and raise it to the 6th power. The other thing that you need to remember for exponents, which is going to help us when we're looking at roots of these complex numbers, is that if you have a radical, let's say the nth root of b raised to the m power, we can write that in exponential form. So whatever root you're taking, that root is, and the exponent is the denominator. So this would be b raised to the m divided by n exponent. So let's rewrite this. I have square root of 3. Because I know I'm going to have power to power, I'm going to rewrite 3. I'm going to write that to the 1/2 power. Times my exponent of 6. And then I have e I 5 pi 18ths times that exponent of 6. So let's reduce this. So I have 3. Well, 1/2 times 6 is 3. So really I have 3 cubed. E I. Okay, let's reduce our fractioned in the exponents. So 5 pi 18ths times 6, well, simplifying, I have 6 goes into itself 1, 6 goes into 18 3 times. So this is going to give me I 5 pi thirds, which is the same thing as 27 e to the I 5 pi thirds. Okay, so there is our exponential form. Let's write this in our rectangular form. To put this in rectangular form, let's first put it into our polar form. So this is equivalent to z equals 27 cis, or cosine of 5 pi thirds plus I sine of 5 pi thirds. So let's think about 5 pi thirds. 5 pi thirds, graphing that, that's going to get me, if I add another pi thirds, that would be 2 pi. So that's going to get me down here in the fourth quadrant, a reference angle of pi thirds. So let's go back and evaluate our trig functions. So I know that cosine of pi thirds is 1/2. Cosine in that fourth quadrant is positive. So I have positive 1/2 plus I. So sine of 5 pi thirds, my reference angle again is pi thirds. Sine of pi thirds is √3/2, but sine in that second quadrant, I'm not second, it's the fourth quadrant, is negative √3/2. So let's go ahead, let's distribute our 27 and rewrite this a little bit. So this is the same thing as 27 halves minus, because of this negative, I 27 √3 all over 2. And so there is our rectangular form of that operation. So now if we're looking at a complex number, instead of just raising it to an integer, we were raising it to a rational function. And this theorem is going to pretty much hold true for DeMoivre's theorem. There's just a little more of a stipulation in here. This is going to equal our modulus of z, so r raised to the 1/n, which is the same thing as the nth root. Okay, so this is the same thing as the nth root of z. But when we're multiplying, so when we do the cis, we have to take our theta. We would have multiplied it by n, our exponent before, but multiplied by 1/n, we get this. This, though, we have to worry, and we have to think about this 2 pi divided by n times k plus I sin theta divided by n plus 2 pi over nk, where k is an integer. And we want our argument which in this case is theta sub n plus 2 pi over n times k, to be between 0 and 2 pi. So when you start plugging in values and we get outside of that range of 0 and 2 pi, then we're not going to look at those as our answers. And we did that before, back in the past, when we were solving trigonometric equations and our argument wasn't theta. There was like maybe n times theta, and we were trying to find all solutions in between 0 and 2 pi. We had to worry about that and did something very similar. So let's look at an example of this. So if it said, find the cubed root of the complex number let's say -8 minus 8i. So maybe we can just say let z equal this -8 minus 8i. And so that means we want to find the cubed root. Another way to write this is the cubed root of z. Or we can write this as z raised to the 1/3 power. So let's first write this in polar form. So we can do so. Let's first graph it and figure out what r is, figure out what theta is. So if we graph that going over 8 to the left and down 8, creating our triangle. So I have 8 here, I have 8 here. So I can find out what r is. R is equal to the square root of 8 squared plus 8 squared. The square root of 64 plus 64. Which is 128. I might be able, I can pull some stuff out of there. That's not a perfect square. I'm just going to leave it like that for now. I also want to find out what my angle is. Let's just look at the reference angle for a second. So if I have tangent theta sub r opposite over adjacent, so 8 over 8, that's going to give me 1. So I know my reference angle is pi force, but I'm in the 3rd quadrant. So theta is going to be this pi here plus my reference angle of pi force. So 4 pi force plus 1 pi force is 5 pi force. So we know z to the 1/3 power is equal to r. Maybe we should just keep it as 128 to the 1/2 power. We're going to raise that to the 1/3 power. Cosine or cis of our angle 5 pi force divided by or multiplied by n, which is the same thing as multiplying by 1/3. Plus 2 pi k over 3. So z to the 1/3 equals, so power to power again is multiplication. So this is 128. 1/2 times 1/3, this is the 1/6 power. This of, let's just get a common denominator while we do this. Anything cancel? No. So this is 5 pi 12ths. I want to get a 12 in the denominator here. So let's just multiply this piece by 4 over 4. So that's 8 pi k.
Should it be 15 pi 12s?
But I'm multiplying. I'm multiplying by 1/3.
Okay.
Did I make something right or wrong up here?
No,
Yeah.
no, it was down there because I didn't realize we were putting it all over 12.
Yeah.
So
Okay. Thank you. Okay, so now we need to look at all of this. So we have the cubed root of z. The third root of that -8 minus 8i is equal to the sixth root of 128 cis of, again, this 5 pi plus 8 pi k over 12. So let's now look at when k equals 0. So if k, I'm going to plug in 0 in here. We're going to get that this is the cubed root of 628, or sorry, the sixth root of 128 cis of 5 pi 12ths. If k is 0, if k is 1, that's going to give me a 13 pi 12ths. So this would be the sixth root of 128 cis of 13 pi 12ths. If k is 2, that's 16, 2 times 8 is 16, 16 pi plus 5 pi is a 21 pi. So we have the sixth root of 128 of cis of, what did I just say, 621 by 12. If I do 3, I'm going to be too big because 3 times 8 is 24. And 24 plus 5, that's 29 pi 12ths, which is bigger than 2 pi. And so our three solutions, three roots of that complex number are going to be these, which if they wanted an exponential form, would just be the same thing, but this would be the sixth root of 128 e to the I 5 pi 12ths. Same thing, sixth root of 128 e to the I 13 pi 12ths. And the sixth root of 128 e to the 21 pi 12ths, which actually reduces, but I'm not going to worry about that for now.